Alright, welcome back. In this video, we're going to go over the Bronsted and Lowry acid-base mechanism. We're also going to be doing a lot of practice problems in this video, so you kind of get a good idea on what these mechanisms look like, and so you can be ready for your exam. I also threw in a challenge problem here, which we're going to do at the end of the video, just in case if your professor likes to be a little bit difficult. So if you're new here, here's how I like to do my videos. I don't like to jump straight into practice problems. I want to explain where this came from. What's the origin of what we're trying to learn here? Because honestly, this material right here is just as valuable as the mechanisms. You'll actually probably find mechanisms much easier if you know the background knowledge to it. So let's start. This is going to be your first mechanism you'll probably ever learn in organic chemistry. This is called the Bronsted-Lowry mechanism. Now first, what is a mechanism? A mechanism is basically a chemical reaction that's diagrammed out. And we diagram it using arrows. So imagine if you have some molecules and you put them in a beaker and you let them interact. Well, how are they interacting? How do we show that they're interacting? Basically, who's communicating with who? What's interacting with what? And we use arrows to describe that. So there were two guys. One guy was named as Johannes Bronsted. The other guy was named as Thomas Lowry, and they noticed something interesting. One day, they decided to put some acidic molecules and basic molecules into a beaker. And when they did that, they noticed something interesting. They would react in a certain way, in a very suspicious way. So first, we need to actually describe what is an acidic molecule. So we're dealing with acids and bases, acidic molecules and basic molecules. So what is an acidic molecule? Well, if you learned in chemistry or even biology, you may have learned about the pH scale. The pH scale goes from 1 to 14, with lower the number being more acidic and higher the number being more basic. Well, when a molecule is more acidic, it contains more hydrogen ions or protons, which is this right here, the H+. Basic molecules contain less of hydrogen ions. And so for example, water, which is in pH of 7, has an equal amount of hydroxide and hydrogen ions. So let's go over this formula now that Bronsted and Lowry discovered. Well, what they're saying is if you were to put an acidic molecule, which has a proton, into a beaker, and then you put a basic molecule into that same beaker, they're going to interact. And what's going to happen is the acidic molecule is going to lose a proton, and the basic molecule is going to gain a proton. So you're probably like, W2F, what does this mean? Let me explain. So I know this is a lot of words, but we're going to go over it slowly. And this will probably make so much more sense than what your professors described. So in a beaker, we're going to throw in one acidic molecule. And then we're also going to throw in one basic molecule. The acidic molecule is called the proton donator. Why? Well, when the acid and base interact in the beaker, one proton will be removed from the acidic molecule and will be transferred to the basic molecule. So the acidic molecule is donating its proton to the basic molecule. That's why the basic molecule is called the proton acceptor, because it's accepting the proton from the acidic molecule. Now, after receiving the proton, the basic molecule is called the conjugate acid, and the acidic molecule, after losing the proton, is called the conjugate base. That may sound a little bit strange, or you may not really understand what I just said right there, but let's go over it. Here's a very basic, simple example of the Bronsted-Lowry acid-base mechanism. So here we have hydrochloric acid. We also have water. We're going to put these two things into a beaker. So the hydrochloric acid is the acid, and the water is the base. So notice at the end of the reaction here, the product side, right? This is the product side. What do we have? Well, we have chloride here, and we have hydronium here. Well, what we did is, see, we have the acid here, right? The hydrochloric acid. Well, what we did is we stripped the proton away, and it became chloride. So what ended up happening is we took this proton, right? This proton right here, and we gave it to the base. Now the base now has one extra proton, and that's why instead of being H2O, now it's H3O, or hydronium. So the acid has now turned into the conjugate base. The base has now turned in to the conjugate acid here. So it's basically flip-flopping here. The acid turns into the conjugate base when it loses a proton. The base becomes the conjugate acid when it gains a proton. A lot of people get this confused because they think, oh, wait a second, the acid becomes the conjugate acid. No, it does not. The acid becomes the conjugate base, and the base becomes the conjugate acid. So I know this is a little bit more complicated, so it'll become so much easier once we do the practice problems. But before we do that, we have to go over some acidic stuff more here. So the most common question that people have, and they ask professors this all the time, is how do you know which one's more acidic? Which of the two molecules that we're dealing with in the reactant side is more acidic? You probably looked at this and you're like, wait a second here. Didn't you say the one with more protons is more acidic? So why isn't the water here acidic? And why is this one not basic? Because remember, we have 2 protons here and 1 proton here. So shouldn't this be the acid? Why is this not the acid? Well, there's another rule. And this rule dominates all other rules. It's all about electronegativity. When a molecule is more electronegative, it is more acidic. This is something you need to know for the rest of your life. So, this column here that I circled in green is called the halogens. They are super electronegative. So on the periodic table, when you go from left to right, the more right we go on the table, the more electronegative we get. Same thing as higher we go up on the table, the more electronegative we get. So these halogens, fluorine, chlorine, bromide, bromine, and iodine, are super greedy for our electrons. They don't want to hold on to protons. They just want to keep all the electrons to themselves and they don't want to share. So let's go back here. Here we're dealing with chlorine and then we're dealing with oxygen, right? Chlorine and oxygen. So let's look at that on the table here. We have oxygen here and then chlorine here. Chlorine is more to the right, so it's more electronegative. But you're probably like, wait a second. Oxygen's higher up, so shouldn't that matter? Well, yes. But first we take a look at what is more to the right. We care about that first. If they're on the same horizon, rather the same level, then we look at how high they are. So say if they were here and here, for example, so the same level up, like the same, like they're as right as, how do I describe this? Okay, they're both in position here, right? They're both in the same position here, right? These two, for example. So you look at the height then. The nitrogen's more electronegative than this. Sorry, I kind of butchered that. But just think, going forward, more right, more electronegative. Okay, so here's the mechanism. So I know this looks a little complicated, so we're going to go over it slowly. I wrote it in words what's happening, but we're just going to go over it here on the actual diagram. So what am I saying here? what did Bronsted and Lowry come up with? Well, here's what they said is the base here, the basic molecule, has a lone pair of electrons. These electrons are going to go and attack the proton on the acidic molecule. So all of this is the acidic molecule here, right? And the acidic molecule has a proton attached to it. So this base is going to use its lone pair of electrons and attack the proton and steal it. It's going to basically rob the acid of its proton. And when this happens, the bond breaks, right? The proton acid bond here breaks, and the electrons go back to the acid. Because remember, bonds are made up of electrons. So the electrons are going to be recycled back to the acid. And that's what we get here. The proton is now attached to the base, and now the acid has lone pairs. Now, if you notice, this is the exact opposite. So notice, in the reactant side, the base has the electrons, the lone pair, but on the product side, now the acid has the lone pair. Now the proton, in the reactant side, the acid has the proton. In the product side, the base has the proton now. So everything's just being flip-flopped here. So let's do practice problems now. Here, we have a reaction here. So draw the mechanism. So first, how do I know that this is the base and this is the acid? So imagine I just erase this, right? Take this away. How do I know what is what? Here's what we're going to do. Here's the cheat sheet. This is all you have to do. You're going to look at the first molecule. You're going to look at the first molecule and then compare it to the molecule that looks similar to it on the product side. So which of these two molecules looks like the first molecule, right? Out of these two molecules, what looks like this? It would be this, right? This is as close as we can get because this matches with this. So we're going to look at this first molecule and we're going to see and compare it to this. What is happening here? What's the difference? Well, we added a proton, right? We went from OH to H2O. So we had one proton here, now we have two. So we added a proton. What does this mean? Well, if we're adding a proton here, remember, if we added a proton, if we add a proton on the product side, we add the proton, that's the base, right? That's the base. So, I'm going to draw this in here. So this is the base, and this is the acid. Because, notice that, now let's compare this and this, right? We lose a proton here. We're losing this proton here. We don't have it here. It's gone. Remember, the acids give up the proton. Acids give up the proton. So this hydroxide is going to steal it. And that's where we gain it. Right, so this becomes the conjugate acid. And this is the conjugate base. I spelled that wrong. Okay, whatever. So now we solved that. Okay, let me just go over it one more time. So just in case if you're lost. We look at the first molecule in the equation. Here's a cheat sheet. Look at the first molecule. Compare it to these two molecules. What does it look similar to? It looks most similar to this molecule, water. All we did is from here to here, we added a proton. We have one oxygen, we have one oxygen. We have one proton, we have two protons. So you must have added a proton. If you add the proton, if you're adding a proton from this to this must be the base because the base accepts the proton. We accept the proton. And this is giving up the proton, right? Notice that we're comparing these two molecules now. From here to here, we're missing a proton. So this must be the acid because the acid gives away the proton. So let's draw the mechanism now. The mechanism goes as follows, right? The base, the lone pair from the base, attacks the proton on the acid, and then the bond breaks. So let's do that. So the lone pair from the oxygen, that's the base, attacks the proton to steal it. Then the bond breaks, and the rest of the electrons go to the nearest atom it can find, which is oxygen here. And that's the mechanism. So let's do the second example here. We have water and methoxide, and it creates hydroxide and methanol. So which one is the acid and which one's the base? So let's do this. Let's do that little cheat sheet. The little trick. We're comparing water, right? Water is our first molecule. We're going to compare it to these two. What is it most similar to? Where there's no methyl group at all here in the water molecule. So it must be this. So we're going from 2 protons here to 1 proton here. So what does this make it? If we lose the proton, since we're losing the proton from water to hydroxide, we're losing 1 proton, so we're going to -1. This must mean it's the acid, because the acid donates the proton. Acidic molecules give away their protons. So we're losing a proton, so we're acidic. So this is acid. It's an acidic molecule. And by default, this must make the other molecule basic. So this is the basic. So if this right here is the acid, this must be the conjugate base. Conjugate base. And this would be the conjugate acid by default. Sweet. There we go. Now, let's draw the mechanism. So the lone pair from the base is going to attack one of the protons. You can choose either one. It's going to attack it. And the bond's going to break, and it's going to go to the oxygen. And that's the mechanism. So now imagine, I'm going to give you a hypothetical scenario. Imagine if, let's say, all of this was not here. How would you know which one's the acid and which the base? Right? You would probably think that since we both have oxygens, that's fine, right? They're equal. But this one has more protons. So shouldn't that make it the acid? Well, no. The reason is let's draw out this molecule. I just erased it, but I'm going to draw it again. So this, I'm going to draw, did not want that. Okay, so let's draw it out. Okay. That's this molecule. That's methoxide. Okay. This carbon is very happy with 4 bonds to it. So it does not want to give up. It does not want to give up a hydrogen. Right? Carbon does not want to lose these 3 hydrogens here because it's happy. Why do we want to edit something that's happy? This water molecule is not too happy. It's basically saying that I'm more happy. This water is more happy losing the hydrogen. Because remember, oxygen is very electronegative. So it wants to keep all the electrons possible. It's easier for this oxygen to lose the proton rather than gain 2 bonds here. This is a little bit more advanced chemistry here, organic chemistry. So it's okay if you didn't understand that, but that's just, a little, just the FYI kind of deal. But since we had this, you can figure it out. Okay. Now I'm going to make it harder. Draw the mechanism, but also fill in the missing molecules. So here we have the first one, okay? Clearly we're missing this one that goes over here, the conjugate. Here matches up with this, clearly, right? So let's draw in this missing molecule. Well, we can't really look at this molecule because we don't have the one to reference it to, right? So we're going to look at this one. How does it match up with this? What's the difference? The difference is we're adding a proton. So if we add a proton, this must mean it's the base because we're adding a proton. Remember, whenever we add a proton, we have one hydrogen, now we have two hydrogens. We're adding a proton. If we add a proton to the molecule, it's basic. This is the basic molecule. This must mean this is acidic. And this becomes the conjugate acid. And then whatever's here is the conjugate base. Conjugate base. Okay, here's what I'm doing. I'm just gonna copy. Oh, wrong thing. Instead of me rewriting it, it's wasting your time. Just copy like this. Oops. I'll erase that. Okay. Well, since it's the conjugate base, this is an acidic molecule, and this is the conjugate base, we erase this, okay, like that. And now this, oops. Okay, there we go. So I basically solved the mechanism without the arrows, just by using process of elimination in a way. But let's actually draw the arrows, because we didn't answer the question. What do? Well, the base attacks the acid, remember. Base attacks the acid. Base attacks the acid. So we're going to do that. So there are electrons here. And these electrons, since this is the base, attacks the hydrogen. And then we shatter the bond here. Let me just redraw this so it makes it the bond. Okay, there we go. So the bond shatters and the electrons get moved over to the oxygen. And that's the first one. What about the second one? Okay, the second one, let's look at what the difference is. Here we have this, and this looks more like it, right? If you look at this is completely different from this. But here and here, what are we doing? We are adding a proton. We added a proton. So since we're adding a proton, this must be the base. And this becomes the acid. Okay, and then this would be the conjugate acid, and this is the conjugate base. Okay, so let's draw the mechanism. The base attacks the acid. So now we can attack any of the hydrogens you want it to. It does not matter. So attack the proton, and the bond breaks, and it goes to the oxygen. And that's the mechanism. Let's do the third one. Now this one is a little interesting. I made it a little bit difficult. So, what is going on? What is the acid and what's the base? I'm going to give you a second to think about this one. I'm doing this to fool you, by the way. Okay, so notice that we have this molecule, and then we're comparing with this molecule. There's nothing to compare with this one, right? There's no nitrogen. So we're comparing this and this. What's happening? Well, all we see is a negative charge, right? We have a negative charge here. The negative charge is implying that we lost something. We lost something. So, this is the acid, and this is the base. How do I know? Well, the negative charge gives it away, but on the molecule itself, remember there's a carbon here, and the carbon has hydrogens to it, right? As 3 hydrogens here. So let me redraw this molecule now, and it'll make it easier for you to look at it and for you to understand it. So let's do that. Oops, wrong color. Does that make it better? So the reason this mechanism works is that, okay, first, this nitrogen here has a negative charge. It has 1 bond, it has 2 bonds, and it's negatively charged. So we have 1 pair here and 1 pair here. The lone pair electrons are going to go over here and attack the hydrogen. The bond will break, and it's going to go to the nearest intersection now, which is that little bump there, because there's no atoms nearby. And when you do this, the electrons get added here, which is what we have here. I didn't draw the electrons, but that's what we technically have here because of the negative charge, right? Now we have a negative charge there. So, now what molecule do we actually end up getting? Well, we get this. Ta-da! Like that. Now you're probably wondering, why didn't we attack the hydrogen here, right? There's hydrogens here, remember? Or here. You could. There's nothing wrong with that. You could. But just for simplicity, I did it as close as possible. All right. Let's do the last one here. How do you know which one's what? How do you know which one's the acid, which one's the base? Because we don't have anything on the product side, so you can't compare it to anything. So what do we do? Okay. So we have to kind of look at electronegativity here. Well, I'm going to tell you that this right here is the acid because we have 2 oxygens compared to 1 oxygen. 2 oxygens are super electronegative. So think about it like this. I want you to close your eyes and imagine this molecule here, right? We have 2 oxygens, which are negative, electronegative. So they're basically trying to gather as many electrons as possible. So this hydrogen here is so far away from these 2 oxygens, it's basically, the oxygens are basically pulling to this side. And this hydrogen just wants to be free. So it's all about electronegativity. You have 2 oxygens versus 1. So more electronegative equals more acidic. So that's the base. So let's draw the mechanism. Attack the proton, bonds break like that. And now we get a product here. Ta-da! That. And then this becomes water. And this becomes the conjugate, oops, let me do it in blue, conjugate base. And this becomes the conjugate acid. Okay. Now for the challenge problem. This medication, dextromethorphan, I don't know, is a cough suppressant, also known as an antitussive. So to increase the shelf life of this medication, they add hydrobromide to it. And this is what it looks like. Dextromethorphan. Draw the mechanism. So you're probably like, wait a second, hold up. There's only one molecule here. Ah, but there's actually two. This is the other molecule. I just didn't draw it there. The reason we draw it on top of the line is because we're adding this in the beaker and then we add this later. We're not adding it at the same time. So all of these molecules here, right, we just did, like this and this, we adding it to the beaker at the same time. Here we're adding it in the beaker and then we add this. It's the same thing. Okay, it's really the same thing, okay? I said it to confuse you. So we can actually draw HBr more like this. All right. Now, what is the acid and what's the base? Well, this is going to be the acid here. Because look at the bromine. Bromine is so electronegative compared to anything on this molecule here. So this must make this the base. Now, what is going to happen? What's going to do the attacking? Because you're probably looking at this, or like, wait a second, we have an oxygen here and a nitrogen here. What's going to do the attacking? If you said the oxygen, you would be wrong. It's the nitrogen. Why? Okay, so this is a little bit more advanced organic chemistry, but we're still going to go over it so you're ready for it on the exam. Nitrogen has 1, 2, 3 bonds already. It needs one more and it's going to be super happy. This oxygen here has only 2 bonds, 1 and 2. For it to be happy, it needs 2 more bonds. It's easier for this nitrogen to grab 1 bond than oxygen to grab 2. So the nitrogen's like, wait a second, stand by, let me get this one. So it fights with the oxygen and the nitrogen wins. So let's draw the mechanism. Attack the proton, bond breaks and goes to bromine. So then we get, oops, I'm gonna copy this. It's too much to redraw it. There we go. Like that. And then these two go away. And then we get our hydrogen here. Now, what about the bromine? What happens to the bromine? Well, the bromine is over here with a full set and a full octet here. Like that. And it's just wandering into space, separated from everything. Right? It's happy like this. Like that. There we go. And this is now called dextromethorphan HBr. Oops, not capital. HBr. There we go. Right? This looks super confusing. But it ended up being really easy, right? This could have been probably one of the easier problems. It looks challenging because the molecule is so big, but it really isn't. And that's what mechanisms are. They're just puzzles. And when you look at it from a smaller picture, right, you look at this, right, and you're like, wow, this is a huge molecule. I'm not going to get this right. This is what professors do. This is a lesson here. Professors like to stress you out on midterms. They're going to put these huge molecules on your exams, and it's going to stress you out. And this is why the averages for organic chemistry are so low, because they get freaked out. Students see this and they get freaked out, and they're like, "Uh-oh, I don't know what to do. I never learned this. I only did it on the easier molecules." It's the same exact concept. It's just a bigger molecule, right? That's exact. And then I proved that it's the same molecule. It's the same concept that we've been doing. It's just a bigger molecule that looks scary, but it really isn't. And that's the lesson I'm trying to show you here is that organic chemistry, yes, people say it's hard, but it's because people are looking at it at a different angle, right? They're looking at it straightforward. You have to look at it from different angles. All of this is just a puzzle. Mechanisms, organic chemistry is just puzzles. But when you find out the tricks, the tips and tricks, organic chemistry can become one of the easiest classes you ever taken. I promise you that. I know I bet you don't believe me now, but if you watch my videos, you will become to believe it. I promise. If you found this video helpful, please like and subscribe. Until next time, later.